Hypothesis testing is a structured decision process used to evaluate a specific claim about a population. A confidence interval estimates a range of plausible values for a population parameter. A hypothesis test does something different. It starts with one clear statement and asks whether the sample data provides strong enough evidence to question that statement. Confidence intervals estimate. Hypothesis tests evaluate a claim. A claim is a statement made about a group. In statistics, a claim usually involves a number and describes an average or a percent. The claim is what we are investigating. It is the statement we are testing using data. For example, a cereal company might claim that the average weight of its cereal boxes is 16 ounces. A school might claim that the average math score is 75 points. A hospital might claim that 40% of patients choose a certain treatment. Each claim includes a number and refers to a large group. A population is the entire group the claim is about. It is not just the individuals we measure. It is the full group that the conclusion will apply to. If the claim is about all cereal boxes produced by a company, then all cereal boxes produced by that company form the population. If the claim is about all students who took an exam, then all of those students form the population. A sample is the smaller group we actually collect data from. Because it is usually impossible to measure everyone in the population, we collect information from a sample. The sample provides evidence. We use that evidence to make a decision about the population. The population is the target. The sample is the source of data. The null hypothesis is the starting assumption in a hypothesis test. It is the statement we assume is true unless the data provide strong evidence against it. The null hypothesis usually represents no change or no difference. It always includes an equals sign. The null hypothesis is written as a statement about a population parameter. When testing a mean, the null hypothesis states that the population mean equals a specific value. When testing a proportion, the null hypothesis states that the population proportion equals a specific value. Hypotheses are always written about population parameters, never about sample statistics. The sample mean and sample proportion are evidence. The null and alternative hypotheses describe the population. The alternative hypothesis represents the competing claim. It is what we will support if the data provide strong enough evidence against the null hypothesis. The alternative hypothesis never includes an equals sign. It uses greater than, less than, or not equal to. If the question asks whether a value is different from a number, the alternative uses not equal to. If the question asks whether a value is greater than a number, the alternative uses greater than. If the question asks whether a value is less than a number, the alternative uses less than. The wording of the question determines the direction of the alternative. A helpful placement rule is this. If the claim contains equality, it belongs in the null hypothesis. If the claim uses greater than, less than, or different, it belongs in the alternative hypothesis. This rule prevents one of the most common mistakes students make. Consider a cereal company that claims the average weight of its cereal boxes is 16 ounces. Because the claim contains equality, it belongs in the null hypothesis. The null hypothesis states that the population mean equals 16 ounces. If we want to test whether the true average weight is different from 16 ounces, the alternative hypothesis states that the population mean is not equal to 16 ounces. This allows for values either above or below 16. If instead we suspect the company is underfilling the boxes, the alternative hypothesis states that the population mean is less than 16 ounces. The null hypothesis remains the equality statement. Only the direction of the alternative changes based on the question. The level of significance is chosen before looking at the data. It sets the standard for how strong the evidence must be before we reject the null hypothesis. Common choices are 0.05, 0.01, or 0.10. If we choose a significance level of 0.05, that means that if the null hypothesis is actually true, about 5 out of every 100 repeated tests would incorrectly reject it in the long run. This is a long-run false alarm rate. The significance level controls the probability of a type 1 error. The sample statistic is calculated from the sample data. If we are testing a mean, the sample statistic is the sample mean. If we are testing a proportion, the sample statistic is the sample proportion. This statistic summarizes the data and serves as the evidence in the hypothesis test. Using the sample statistic, the software calculates a p-value. The p-value is the probability of observing a sample result at least as extreme as the one obtained, assuming the null hypothesis is true. The assumption that the null hypothesis is true is built into the calculation. Another way to understand the p-value is to imagine repeating the same sampling process many times under the assumption that the null hypothesis is correct. The p-value tells us how often we would see a result this extreme just by random chance. It measures surprise. A small p-value means the data would be rare if the null were true. If the p-value is small, the sample result would be unusual under the null hypothesis. That provides evidence against the null hypothesis. If the p-value is large, the sample result is not unusual under the null hypothesis. The data are consistent with the null hypothesis. The decision rule compares the p-value to the significance level. If the p-value is less than or equal to the significance level, we reject the null hypothesis. If the p-value is greater than the significance level, we fail to reject the null hypothesis. This comparison turns evidence into a formal decision. Suppose we test the serial box claim and obtain a p-value of 0.02. If the significance level is 0.05, the p-value is smaller. Because such a result would be rare if the true average were 16 ounces, we reject the null hypothesis. When we reject the null hypothesis, we write the conclusion carefully. We say there is sufficient evidence to support the alternative hypothesis. We restate the conclusion in context, referring to the population and the parameter. Now suppose the p-value is 0.20. If the significance level is 0.05, the p-value is larger. The result is not unusual enough under the null hypothesis. We fail to reject the null hypothesis. When we fail to reject the null hypothesis, we say there is insufficient evidence to support the alternative hypothesis. We do not say that we accept the null hypothesis. We do not say the null hypothesis is true. Failing to reject means the sample did not provide strong enough evidence. It leaves open the possibility that a real difference exists, but was not detected. A small sample or a small true difference can lead to failing to reject the null hypothesis, even when it is false. This connects to the idea of misdetection. Weak evidence does not prove the null is true. It simply means the test did not detect a difference. There are 4 logical possibilities in a hypothesis test. The null hypothesis can be true or false. Our decision can be reject or fail to reject. 2 of these combinations are correct decisions. 2 are errors. A type 1 error occurs when we reject the null hypothesis even though it is actually true. This is a false alarm. We conclude there is a difference or effect when there is not. The probability of a type 1 error equals the significance level. A type 2 error occurs when we fail to reject the null hypothesis even though it is actually false. This is a misdetection. There really is a difference or effect, but the sample did not provide strong enough evidence to show it. Larger samples make type 2 errors less likely because they provide clearer evidence. Consider a smoke alarm example. The null hypothesis states that there is no fire. The alternative hypothesis states that there is a fire. We begin by assuming no fire unless evidence suggests otherwise. If there is no fire and the alarm stays silent, that is a correct decision. If there is no fire and the alarm goes off, that is a type 1 error. It is a false alarm because we acted as if there were a fire when there was not. If there is a fire and the alarm goes off, that is a correct decision. If there is a fire and the alarm stays silent, that is a type 2 error. It is a misdetection because there was a real fire, but the system failed to detect it. The full hypothesis testing process follows a clear structure. Start with a claim about a population. Identify the population parameter. Write the null hypothesis as an equality statement. Write the alternative hypothesis based on the direction of the claim. Choose a significance level. Collect a sample and compute a sample statistic. Use the p-value to make a decision. Write a conclusion in context. stating whether there is sufficient evidence to support the alternative hypothesis. Hypothesis testing allows us to evaluate claims using data, while recognizing that decisions are made under uncertainty and that errors are always possible.